right, guys, I knew you'd be back. You just can't get enough of that graphing, huh? Well, now let's talk about some very specific graphs. Graphs that, in large part, at least in this section, will be created by dots or lines connecting those dots. So, the first one to talk about is one that we'll use a lot in the next section of the course when we discuss correlation or regression. It's what's called a scatter plot. Okay? A scatter plot simply takes two interval variables, right? Something like in this example, a grade on an exam or in a final grade in a class that might range from 0 to 100, and the number of hours you studied for that exam or for that class. And what we tend to see is that, let's say I collected data from 20 people. And so I asked all of you at the end of the semester, can you estimate how many hours you spent studying for the last exam? And then I plot the data. I say, John, you told me you studied this much. This is your score on the exam. That's your X and your Y, right? The two pieces of information I know. And I go around and I get it from everybody, right? Miriam, Zainab, all of you, I get it all. And then I place them into a list of X and Y coordinates. You guys have looked at coordinate space before, right? You know how X and Y axes work. So you just move up a couple of spots on that X axis to whatever the score was. So hours studied, I place my graph down, put that line down and mark off 1, 2, 3, 4, 5, 6, however many hours studied it goes up to, right? Put the whole range down in there. Do the same thing on the y-axis. Put the whole range of the scale, 0 to 100. And then I start putting a dot for every individual. John, you're 8 hours and 75 on the exam. And Billy, you're 12 hours and you're 87 on the exam. And then what I do is I step back and I look at the dots. And I see whether or not the dots appear to demonstrate some pattern. Do they group in some way? Remember, the whole point of the graph is to visually display your data in a way that may make patterns more clear. And so in a scatter plot, we can look to see whether or not these dots appear to fit a line. Many times you'll see these very clear linear relationships that go up and to the right, or down and to the right. Or sometimes you'll see nonlinear, curved relationships. And you can sort of see these very easily in a scatter plot where you can't see them so easily in raw numbers. Now, you might notice in this case that the lowest grade that anybody got on an exam was a 40, and so that bottom portion of the graph is just completely empty. Oftentimes what we will do is actually just get rid of that portion of the graph. So in what's called a range frame, we would just erase that section, and then we take the x-axis and we move it up to the top. Right? Now, oftentimes you will see that when that's done, the y-axis right below 40 will have a break. They'll leave a small gap so the line doesn't go all the way to the x, sometimes even putting some little lines to the side to space it. That's supposed to just indicate that the entire y-axis has not been represented there. A section has been deleted because there was no data in that range. Okay? So, scatter plots are really easy, right? As I said, you organize the data per participant, keeping the participants' data together. Everyone's got two scores, an X and a Y. X is going to be your independent variable. Y is going to be your dependent variable, right? So organize them as such. Draw your axes, mark off your demarcations for the actual scale, label your scales, and then place your dots. And when you're done, you have got yourself a scatter plot. If you'd like to make the range frame, simply delete the section of the graph that has no data in it and move your axes up accordingly. So here are our data, actually. There's a few of you missing because I grabbed this before everybody was done, and some of you actually didn't go back yet and put it all in. But these are the data that you guys gave me on your age and your approximate height in inches. We don't really show a strong pattern here. It may be a very, very slight positive correlation, but we'll talk about that when we get to correlations, showing that as age increases, height slightly increases. We tend to not see that strong relationship in people of our age because we're adults and we're largely fully grown. But as children, height and age definitely would show this strong linear pattern. Whereas one was increasing, the other increases. 10-year-olds are taller than 3-year-olds. By and large, right, on average. And so you can really start to see these, what are functionally linear relationships, right? So linear relationships mean straight line. Even though a curved line sounds like it still has the word linear, it'd be called a curvilinear or just a non-linear relationship. The good thing about a scatter plot is that you can see either one. So if I had lots and lots and lots of dots, let me say I had you do a simple task. Have you ever done the ruler catch task where you've got a ruler in your hand, someone else is holding it, you're not touching it, they drop the ruler and you catch it as soon as you see it drop? Right? And they just measure where on the ruler you caught it so we can see how far it dropped before you were able to get it. Sort of a measure of reaction time. What if I did this at the lowest level of arousal? So I grabbed 20, 30 people and I had them do this task a bunch of times when they were just barely awake, almost comatose. Probably falls through every time, right? Really, really terrible performance. But as they wake up a little bit and arousal goes up, they start to get better and better and better and better and better. And so faster and faster reaction times. And then, as they get more awake, because now I start giving them coffee and more coffee and more coffee, they start to get jittery. And their performance starts to go down and down and down. That particular curvilinear, nonlinear relationship is called the Yerkes-Dodson curve. And it basically says that our performance on a task is best at this mid-level of arousal, but starts to deteriorate when we are either so low in arousal that we are near sleep, or so high in arousal that we are near panic. Another thing scatterplots allow us to see really easily, and not just scatterplots, you can see these in bar graphs and a number of other figures as well, are outliers. What's an outlier? Well, visually you can see it here, right? It's that piece of data that doesn't sit with the rest of them. We talked about it before as if you looked at your whole range of data, and most of your data sat within, let's say, 40 scores, and then there was this other one that was way out here, so everybody scored between a 60 and 100 on the exam, and then somebody got a 7. That 7 doesn't fit with the rest. That's an outlier. And visually, we can really start to see outliers in scatterplots and other graphs. Now, the question is what you do with an outlier. Well, first of all, in this class, you leave the outlier in the data set. For all your calculations, I don't care if it is an outlier or not, you leave it in there, okay? Unless I tell you to take it out, do not do anything with an outlier. But if you're talking about practical and it's your data and you see this outlier, the first question is probably, did I make a typo? Right? If I'm measuring heights and I was typing in all of your heights into that set of data to be able to create that figure, and somebody came out as a 700 inches, that's way too big. That means I probably hit the 0 twice, right? And you were really only 70 inches in height. So sometimes the outlier is just a typo and you can go fix it. The next question is, if it's not a typo and it really is part of the data, is it taking away from a meaningful relationship? Did I measure running speed among a group of random people I picked off the street, and one of them happens to be an Olympic track athlete? I didn't know that, but then they run way fast, and I say, wow, the average running speed of not your normal American is really pretty damn fast. Then in that case, I'd probably want to leave that person out because they're not your average American. So how far does it have to be? Well, mathematically, we often use the 2 or 2.5 standard deviations before we decide to throw out an outlier. Again, we're not going to do that in this class, so don't get too worried about that. Another question could just be, did you have a goofball in your study? Right? Maybe somebody behaved weirdly, and that's why it's an outlier. Somebody who studied a ton, spent 40 hours studying, but they were studying really poorly and had the TV on and all this other stuff, and so they don't sit with the rest of the data, but it's because they were sort of goofing off. And then lastly, sometimes it could actually be an important clue. What if that person who didn't study at all and got a really high grade, even though pretty much everybody else, you got a high grade if you studied, you got a low grade if you didn't. This one sat out from the pack in the good way. They studied almost none and still got a great grade. Maybe that tells you about how they studied, or studying them more and asking that person questions might allow you to learn something more meaningful or some clue that really shouldn't be ignored. So outliers are important. In this class, we're keeping them in with the data, and we'll calculate them just like they're part of all the rest of the raw data. So if we take those dots and we connect the dots, which is always fun, then we have a line graph. Right? Line graphs are really easy. In this case, the sense of urgency to get out of bed. You ask a bunch of people, on a scale of 0 to 10, how much does your alarm clock push you to get out of bed? 1. How about when the snooze comes on? It's still a 1. How about when it's the second snooze, okay? Yeah, okay, I'll give that a 2, maybe a 3. I'll stay around there for the next couple of snoozes. But what if, and I have cats, you start to hear your cat coughing up a hairball about to barf on the bed? Whoa, all the way to a 10, right? And so you take all these data, you plot them in, and then you just connect them with lines. And it shows starkly the change in urgency to get out of bed as a function of that change in the x-axis, right? You can also use line graphs, these dotted line graphs, to represent change over time, right? So the number of gun murders in Canada between 1961 and 1994, the year, the data, the year, the data, the year, the data. It's functionally, in this case, like a scatter plot. You only have one set of data for each year, unlike with some other data where you might have 7 people that were 15 years old and 12 people that were of that height or things like that, right? And so we're simply presenting data as a function of time now. So you can see how that y-axis changes over time. Generally speaking, gun murders have gone up in Canada between 1961 and 1994, despite some fluctuations in between. Right? And so again, time series plots are really just an example of a line graph that's used time on the x-axis, right? Some increment of time. So let me tell you about, I guess, the real importance of graphing from a sort of tragic story. You probably don't remember, in fact, chances are you really don't remember, the Challenger explosion. Okay? The Challenger exploded in 1986, I believe it was. I was only 4 or 5 years old. I grew up in Miami, and because Cape Canaveral was where a lot of these rockets and shuttles took off at the Kennedy Center, that was only a few hours north, and we used to watch the launches of the space shuttle on the closed-circuit television in the classroom. And then as soon as it took off and it was no longer visible on the TV screen, all the classrooms would unload out into the playground, and we'd look up until you could spot the shuttle and you'd be able to see the trail of the rocket heading off on its way to space. Very neat. Thankfully, I was not out there watching this one that particular day. I wasn't yet in elementary school. And so the Challenger blew up. It blew up shortly after takeoff, in fact. And it was found later on that it was due to damage or erosion of a particular O-ring, a type of gasket that held pressure between one section and another. And so the question is, why did this happen? Did we know about it? Were there any warning signs? So this is a graph that the NASA engineers delivered to the NASA administrators on the night before the launch. The administrators were a bit concerned because it was supposed to be pretty cold that day at Cape Canaveral, somewhere around the mid to upper 20s, right, below freezing. Now, I know as a Michigander, you're going, 20s. Well, okay, I'm from Miami. That's cold. That's really cold to us. Hell, I'm sitting here in a blanket, actually, that you can't see because I'm cold even in the 60s of my basement. And so the 20s are really cold for Floridians, and they looked at it and said, should we be worried about the launch? So they wrote down to the NASA engineers and said, can you let us know what data we have on damage to the various rockets that we use to propel the shuttle at various launch temperatures? And they said, okay, no problem. So they got together all the data, figured out a way of presenting those data into a graph, and they came up with this. Okay, so on the left-hand side, what you're really looking at is simply an indicator. It's like a legend or a key for how to read the right side of the graph. So you've got 2 different types of motors that can be on that shuttle. You have a 1-stage and a 2-stage, an A or a B rocket, let's say. So what they did was they tried to represent for each launch. So you can see, if you look to the right, and all these pairs of rockets, you see 1A, 1B, 2A, 2B, 3A, 3B, 4A, 4B, and so on. The 1, 2, 3, 4, that's a particular launch. And you can see, for each launch, they've written the temperature that it was that day on the A-stage rocket. So on the very first launch there, it looks like it was 66 degrees. And you see there's 0 other information written on that rocket. And if you look over at the codes, nothing on the rocket means no damage. 70-degree day, we get an E with some lines, looks like primary O-ring erosion. And so what they've done is given you an indicator of every temperature at every launch and what damage occurred given those temperatures. So pause it if you need to, but take a look at this and see if you can discern a pattern. Can you tell if the NASA administrators should cancel the launch or should continue the launch based on what you see here? How about if I take the data and I present it in a different way? So what we're looking at is temperature. That's relevant, right? Which launch it was and whether it was an A or a B stage rocket, none of that's relevant. Really, it's just the temperature and what kind of damage. So let's call the damage sort of a 1, 2, 3, 4, 5 kind of a scale, right? Or it can be all the way to a 12. I don't really care. But let's numerically rate that so that we can put that on the y-axis. A degree to which the O-ring is damaged. None to a lot. And then on the x-axis, we'll just put temperature. And then we create a scatter plot. Okay, so here's your scatter plot of those data. You can see all the dots over there on the right-hand side of the figure. As the dots go up on the y-axis, that's more and more damage to the O-ring. As the dots move left or right on the x-axis, that's moving colder if the dots are closer to the left, warmer if the dots are closer to the right. So just looking at those dots right there, if you were to draw a line that was the best fit into that cloud, you'd probably draw it from somewhere around the x-axis at maybe 75-ish, up towards that SRM 15 you see up there, where the O-ring damage was really, really high. And what you're showing there with that shape of a line is that as the temperature went up, the degree of O-ring damage tended to go down. As the temperature went down, the degree of O-ring damage tended to go up. So out of all these data, the coldest day that it was, the only data we have for coldness here is for 50 degrees. The launch was projected to be 26 to 29 degree range, forecasted temperatures. That's well outside of the range of data that we tested in, but if we were to carry that line back all the way to where 25 or 30 would be, we would go way past the 12 on the degree of damage to the O-ring. If these data had been presented to the administrators, then it's most likely the case that they would not have launched. But the NASA engineers working on data that were provided to them by Morton Thiokol, the company that made the rockets and also makes the table salt with the girl with the umbrella, the Morton Salt Company, that company gave them these data, and that was how the engineers had put together those data. Sort of a tragically bad graph, right? Because it resulted in the death of these individuals and the loss of both of life and money for tons, right? And the real blow to the NASA space program in so many ways. All because somebody didn't know how to put data together in a way that was easily readable, that demonstrated that pattern. Okay, so hopefully that sort of really reinforced why understanding and knowing how to create graphs is so damn important. In just about any field you might end up in, you are likely to either have to interpret a table or figure or to create a table or figure. So in the next video, we'll finish things up by showing you a few more graphs, some bar graphs, tell you how they differ a little bit from the histogram that we've already discussed, pie charts, and pie charts suck, but we'll cover them anyway. And then we'll wrap it up with some box and whisker plots and a little sort of cheat sheet on what graph to use at what time. All right, cheers.